Hello everyone and welcome to the presentation of PaaT, PaaT as a thing. So, owning a pet comes with many benefits, but losing a pet can be a heartbreaking experience, and unfortunately, accurate statistics on lost pets are hard to come by due to the lack of national reporting system. However, in 2009, it was estimated that around 33% of all dogs and cats in the USA go missing at some point in their lifetime, resulting in close to 10 million lost or stolen pets every year. And the problem becomes even more disheartening when we consider that less than 23% of lost pets are reunited with their owners. In 2016, nothing changed. And we can see also that in 2022, missing pets recovery stats says that cats are the pets that usually are not found. And if they are found usually outside. Moreover, traditional methods of finding lost pets, such as identification tags or microchip, have limitations. Studies have shown that these methods are only effective in a small percentage of cases, ranging from the 2 to the 10%. One possible solution to address this issue is to utilize a GPS-based pet tracking system. While such systems already exist, they often have drawbacks. For example, the modules used in the system cannot be easily repaired if they malfunction, or the accuracy of location data is compromised in areas with poor satellite signal reception and no information is given to the user. And to tackle these challenges, an IoT-based GPS system for pet tracking can offer a comprehensive solution, providing improved recovery rates, continuous monitoring, remote access, integration with other devices, and data analytics. To meet user requirement, the pet tracking system should remain active for at least 24 hours in case of a pet getting lost, and for at least 1 or 2 weeks if the pet remains inside the geofence. Also, the system should update the pet position every 5 minutes if the pet is lost and is outside the geofence, while 60 minutes can be a good trade-off between tracking accuracy and energy efficiency. Also, the accuracy is important. 10 to 50 meters can be a sufficient range for users to locate their pet, and is crucial to detect false positive and false negative to ensure reliable tracking result. Security is also paramount, with data exchanged by the application that needs to be encrypted to protect sensitive information such as the pet's position from malicious attacker. Finally, since data transmitted are in the order of 2 to the power of 7 bytes, and since we need that the system has to be energy efficient, and since we need that communication has to be in the order of 10 kilometers, LoRa is strongly suitable for our system. So this is our proposal path. To use the system, pet owner attaches the GPS device to their pet's collar or harness, and the device is battery powered, and its battery life depends on whether the pet is inside or outside the designated geofenced area. And pet owner can access the system through a web interface where they can view their pet's location, movement history, set up geofencing, receive email alerts when their pet leaves the designated area. The pet tracking system network architecture consists of several key elements. We have the LoRaWAN protocol that enables efficient communication between devices. MQTT, a lightweight messaging protocol, facilitates seamless communication between the cloud service and the AWS IoT core. And the Things Network Stack integrated with MQTT enables data transmission from the pet tracking devices to the AWS IoT core. The system utilizes IoT devices with a Riot OS, that is a real-time operating system designed for resource-constrained IoT devices. TTN serves as the LoRaWAN infrastructure provider, ensuring secure and reliable communication between IoT devices and cloud service. Python and TTN client is used to configure geofence boundaries, enabling precise location definitions and updates. Finally, we have the Amazon Web Services components. We have a AWS IoT Core that serves as the central hub for device cloud communication, DynamoDB to store pet location data efficiently, Lambda function to handle encryption, decryption, and data processing, AWS Amplify for web application development, and API Gateway that acts as a secure entry point for seamless communication between the web interface and the backend services.
This is the fritzing circuit, in which we can see the connection between the ESP32, that in our case is the Heltec LoRa 32V2, the GPS sensor, and the 2 actuators, the buzzer and the LED light built in the board. The main sensor of the system is the GPS module, which in our case is the E108GN02. This sensor is particularly accurate also because it does not suffer from temperature changes, as we can see in the bottom right graph. It has an accuracy of 10 to 15 meters, which is sufficient for our purpose. LoRaWAN is an industry standard protocol specifically designed for low-power wide-area networks. It enables long-range communication between devices while consuming minimal power. The utilization of LoRaWAN in the pet tracking system ensures that the location data from the ESP32 and GPS module can be transmitted efficiently to the cloud service. Those properties make it especially suitable for this project. Moreover, LoRaWAN operates in the licensed spectrum, ensuring cost-effective deployment and scalability, instead of nowadays solutions. A fundamental aspect is that LoRa divides the devices into main classes, Class A and C. A device of Class C is a device always active to listen for new messages. These kind of devices are basically the antennas. On the other hand, the devices of Class A corresponds to our system because they preserve power consumption and could be used with a battery. The crucial aspect is that the communication Class A devices is always initiated by the end device. A device can send an uplink message at any time. Once the uplink transmission is completed, the device opens two short downlink windows. If the network server does not respond during these two receive windows, the next downlink will be after the next uplink transmission. Our initial idea is to give the possibility to the end user to turn on or off the buzzer and light when the PaaT is outside the geofence. But given this aspect of Class A devices and the length of LoRa messages, we abandoned it because we could not send this information and GPS data in a single message, and use two messages is a risk because the system could not receive the response for the first message and get stuck. To evaluate the LoRaWAN connection, a specialized tool offered by Fit IoT Lab was utilized. The developed code for transmitting data was uploaded to the tool, and a series of tests were conducted. The results of tests demonstrated the performance of LoRaWAN connection, with specific attention given to power consumption during data transmission. The graph reveals distinctive peaks in power consumption corresponding to message transmissions. Notably, the highest peak corresponding to the sending of messages, while the smallest peak aligns with the reception of response messages. Here we can see in detail the two peaks, and calculate the consumption of the messages. We just calculate the area delimited by the lines.
The table shows the consumption of each component of the system, measured from the data declared by each manufacturer and verified with tests performed with IoT Lab and the digital multimeter. The board has a constant consumption of 50 mAh all the time the device is on, since in this first experiment it was not possible to introduce a form of power saving due to the limitation of write OS. Communication via LoRaWAN has a negligible consumption because of the extremely low transmission and reception time and the few messages exchanged, 1 every hour inside the geofence and 6 every hour outside it. The GPS is the component whose operating time is least predictable. In fact, it is difficult to predict how long it takes to obtain a reliable position due to external factors such as shielding from satellites. The minimum turn-on time is 10 seconds, the time of the first check on satellite coverage, while after 100 seconds the sensor is turned off if it fails to detect a reliable position. We placed ourselves in a worst case with consumption of almost 1 mAh for a 100 seconds power on. The LED and buzzer in this first configuration remain off as long as the device stays inside the geofence, otherwise they are always on until it re-enters the geofence. The total consumption obtained is almost 51 mAh inside the geofence and almost 85 mAh outside it. From the sampling time considered, it is possible to move to a comparison with different assumptions. In the case where the sampling time was reduced from 1 hour to 30 minutes inside the geofence, an increase in consumption of less than 20 mAh for 1 day would be obtained, making a higher communication frequency more convenient. On the contrary, battery can be saved by reducing the sampling time outside the geofence, but would lose in system accuracy. This new scenario introduced the possibility of putting the board into deep sleep, when no sensor or actuator is active and there is no communication. The deep sleep mode allows to drop the consumption of the board to only 1 mAh. A second power-saving modification is the inclusion of a cycle, 0.4 seconds on and 1 second off, for the LED and buzzer. The total on time in an hour becomes less than 1/3 with a saving of about 21 mAh each hour outside the geofence. These new considerations completely change the total consumption scenario, leading to greatly reduced consumption inside the geofence to only 67 mAh instead of 1,223, and a reduction of about 500 mAh per 24 hours outside the geofence. A 2,400 mAh capacity battery could cover up to 35.5 days inside the geofence and 1.5 days outside. The working prototype of the device made it possible to verify that the power consumption is in line with that claimed. The GPS has two different power consumptions, 35 mAh for searching and 20 mAh for tracking, respectively. Only the first value is of interest in the project, since the system turns the sensor off as soon as it registers a reliable position. For the choice of battery, it is necessary to find a compromise between total capacity, size and weight to avoid the color being uncomfortable and painful for the pet. For this reason, the choice fell on a 2400 mAh rechargeable battery instead of the classic AA batteries. We spent most of our time fixing the code because we had some problems with the WART configuration in Riot, which we fixed thanks to Andrea Vitanetti and had to adapt the external MinMea library to parse output of the GPS sensor. We would have liked to add the accelerometer to recognize the pet's movement, and we consider this feature for future development. The project can be expanded also by solving the problem of deep sleep implementation in Riot, and last, the sampling time can be made fully configurable by the end user, leaving the freedom to choose between accuracy and energy saving. You can find all references to the project in the description. We thank you for viewing.